It's a real pleasure to speak in this room if I don't get completely trapped by the equipment. So I have chosen a subject for you which shows, well, on the one hand shows somehow the unity of mathematics, that, I mean, what you may approach mathematical problems from different points of view, coming from different subject areas of mathematics. And of course, since I was asked to speak about something which is close to my own research, I mean, I won't speak about anything I have discovered myself, but at least about concepts which are related about what I'm doing. So there's one basic definition for this whole lecture, and this is due to Emil Artin. The definition is Artin's, but I think the notation came later, and it's the following. So you call a field K a C1 field, a CR field, if, so here R is an integer, non-negative integer, if every K form, so what's a K form? It's a homogeneous polynomial with coefficients in K, okay, right? So yeah, it's like this. And you know what homogeneous means, right? So all terms have the same degree. And of degree D in n strictly larger than d to the r variables has a non-trivial zero in k to the n. So what does non-trivial zero mean? Well, I mean, you can plug in elements of k in the polynomial, and, well, there is the trivial zero. If you plug in 0, 0, 0, 0, then you obviously get 0, since the polynomial is homogeneous. So non-trivial trivial zero is anything else, right? So the question is whether this holds. Now, I'll tell you a bit later why Artin was interested in this property. But I mean, you may say that it's interesting in itself, so let's pretend it. And so before, so we shall mainly consider in examples for low r, and let us consider examples for small r's. So what about r equals 0? So what are C0 fields? Can you tell me the answer? So which fields are C0 fields? Exactly, yeah? Algebraically closed fields. So by definition, a field is algebraically closed if any polynomial in one variable, not necessarily homogeneous, has a 0, but then it follows immediately from this that any homogeneous form and of at least two variables also has a 0. You just fix some variables and you get a polynomial in one variable. And there's nothing more. I mean, the condition tells you. So for r equals 1, you come to C1 fields. So then this says that I just repeat the definition that every K form of degree D in n strictly larger than d variables has a non-trivial 0. And so Artin asked, So Artin had a candidate for these fields, and the first candidate he had was finite fields. But he could not prove it for finite fields, and so the first person to prove this for finite fields was Chevalley. So this is Chevalley's theorem. That finite fields are C1 fields. So, since in my view, every decent mathematical lecture should contain a proof, at least one, so maybe it's a good moment to give a proof of this, although many of you may have seen this already. And so the proof, in fact, is not the original proof of Chevalley, but it contains improvement by Warning and also by X. And in fact, so this was in the golden days where I mean there was no publish or perish industry, and in fact these papers, both the paper of Chevalley and the paper by Warning, was published in the publications of Hamburg University, where Artin was a professor. And of course, Chevalley's paper was in French and Warning's paper was in German, and they were published one after the other. So this, I think, this would not happen anymore today, unfortunately. So how do you do this? So let FQ be the finite field with Q, that is P to the R, either P to the M elements. And so P is the characteristic of the field, and so we shall prove every polynomial equation f of x1 xn equals 0. So the point is that not necessarily homogeneous. I forget about the property of being homogeneous. So so for every equation, the number of solutions in fq to the n is congruent to 0 modulo p if d, which is the degree of f, is strictly smaller than the number of variables. And so, as you see, if I prove this, then I have the theorem, because the homogeneous equation will always have the trivial solution, and therefore, there must be at least one more. Okay, and so there is a notation. So if G is a polynomial in n variables, then so this number of solutions I shall, so maybe here I shall write that this I shall denote by n of f. And I shall also use the notation sigma of G to be the sum of the values G of alpha 1, alpha n to the q minus 1, where alpha 1 and so on alpha n. So when we run over all n tuples of elements in FQ. Right? And so what we know is that alpha q to the q minus 1 is 1 for all alpha in FQ. So what we have here in the sum, in fact, are only zeros and ones. So in particular, you have this, that this element here is actually already in the prime field. right? So this is a field of characteristic P, so you're adding 1, so you get a number which is smaller than P. Huh? And moreover, what you have is that if you look at Qn minus sigma G, then it is the sum for all alpha 1, alpha n of 1 minus G alpha 1, alpha n to the Q minus 1. And this is congruent to Ng modulo P.
Maybe in the previous time you should say that alpha is not zero.
Thank you. So yeah, this is just what these are all potential solutions, and sigma g is where you have solutions, and you are adding here ones whenever you have a solution, and you're adding here zeros when you don't have a solution, right? So that's why it holds. So it is enough to prove that sigma of f is 0 for our particular f over there, because then we'll have the theorem. Okay, and so we shall write this which one? Yeah, f x1 xn to the q minus 1 as a linear combination of monomials. So x1 r1 and so on, xn rn, like this. And so it will be enough to prove that for all of these monomials, x1 r1, xn rn, the sigma is 0. Because if you have this separately for each monomial, then by linearity you will have the theorem. And so then, well, this is just a calculation now. So if Ri is 0 for some I, then this is obvious because you are summing over a whole residue class. And also, so otherwise, we may assume that one of the Ri, say R1, is strictly smaller than Q minus 1. So why is this so? Well, this is, well, pigeonhole principle. We suppose that the degree is smaller than n. So one of them should then be smaller than Q minus 1. And then I fix an alpha to alpha n in fq to the n minus 1. And the observation that I make is that if you look at the multiplicative group of the finite field, it's known to be a cyclic group. So it is generated by one element, call it omega. And so then what you are doing here, that if you fix these alpha 2s and so on, you are summing first some alpha r1 and then alpha 2 r2 alpha n r1. But so here, of course, the second term comes out, and so you are just having summing over the r1's powers of alpha, and this sum can be written as omega to I or 1 from I going to 0 to q minus 2, right? Using that the group is cyclic. But this you can compute using the geometric series. This is omega to the r1 to the q minus 1 over omega to the r1 minus 1. And so that's 0 if 0 in FQ. Okay, so if for each fixed n minus 1 tuple this is 0, then the whole thing is 0 and we are happy. Okay, so that was the proof of this lecture. So now I'm relieved, and in the remaining time I shall only sketch the ideas.
So the proof wouldn't go over if all of them would be q minus 1, right?
No. Yeah. That's the point. In fact, then it's not true. I mean,
Yes, I see.
yeah. Okay. So this was the first example of a C1 field. Now, so other examples of C1 fields. So one is a famous example due to Zen, which is the field of rational functions over an algebraically closed field. So for example, you take the complex numbers. So actually this is also not very hard to prove, but the best way to prove it is using some elementary algebraic geometry. So usually when I'm teaching elementary algebraic geometry, I give the proof. But there exist proofs without algebraic geometry as well. Okay, and so so this is Lang and maybe Greenberg, is that when you take the field of formal Laurent series over an algebraically closed field. Now I'll make some comments about what this gadget is. So this is the fraction field of the field of formal power series, which everyone knows what they are. I mean, everyone has seen a power series already. And so in fact, the elements of this can be written as sum of AITI, well, AI are in K, where this I starts from some possibly negative number. So it's not completely trivial to see why this is so, because I mean, if you take the quotient of two power series, it's not completely obvious why you can write it in this form. But I mean, for later use, I'm explaining this for later use, so I point out why this is so. Well, this is simply because if you take a power series, let's call it alpha, then you can always write it as t to the I times some power series, let's say j equals 0 to infinity aj t to the j, where the leading term is non-zero. And if the leading term is non-zero, then you can prove easily that a power series is invertible. So you can find by using indeterminate coefficients, you can easily prove that it has an inverse. So then it's obvious that if this is invertible, then when you divide out by this t to the I, then there will be finitely many negative coefficients, but after that it will stop. Okay? And so for later use, let me point out that so if you take this power series, and AIT to the I, and you associate to it the minimum, the smallest I, such that AI is non-zero, then this defines what is called a discrete valuation. So let me call this VT from k t to z union infinity. It's 0, which has the value infinity by definition. And this Vt has the property that Vtx times y is Vtx plus Vt of y, and also Vt of x plus y is at least the minimum of Vt of x and Vt of y. Okay? So this is the largest power of t with which it's divisible, but it may be negative. Okay, so this is what is called a discrete valuation. Okay, and so one last remark about this theorem is that, so Lang actually proved the following, that if K is a CR field, then it follows that K of t and also K double bracket t are CR plus 1 fields. And so, well, since algebraically closed fields are C0 fields, then well, this implies what I've written, the theorems of Zen and Lang-Grimberg. Now, this was in fact the doctoral thesis of Serge Lang. So if you have seen the name of Serge Lang before, this is actually what his first subject was. It was a thesis whose supervisor was Emil Artin, of course. But it is Lang who did the work. And so this is not so hard to prove. Well, it's not trivial, but not very hard. Basically, you reduce the case of power series fields to the case of rational fractions by an approximation argument. And this approximation argument is what was done by Greenberg in a much simpler way than Lang actually did. But Lang also had a much more difficult theorem in mixed characteristic, but that I will come to that a bit later. Okay, so it's time to tell you why Artin was interested in this property. So Artin's interest in C1 fields was the following. That over a C1 field, there is no finite dimensional division algebra whose center is K. So if my C1 field is K. So what's a division algebra? Well, it's also called skew field. So it's like a field, except that its multiplication is not necessarily commutative. But it's better to call it division algebra because I want to emphasize the fact that, so I don't know, there is this division algebra D, which contains K, and it's finite dimensional over K as a vector space. So it's an algebra over K. Okay? And so in particular, if you know Chevalley's theorem, it will imply to you that every finite division algebra, finite skew field, is necessarily a field, which is the theorem of Wedderburn's. Proven originally by a different method, and yeah, because it's also always finite dimensional, of course, over its center, which is a field. Okay, so this is one way to prove this kind of statement. And in fact, another way to phrase this result is that there is a very important object in algebra which classifies division algebras, finite dimension over center. It's called a Brauer group. So this is something which comes up regularly in my work. I've written a book about this and also using it regularly. And so every such D corresponds an element in this Brauer group. So in this case, it says that the Brauer group of a C1 field is just trivial. It's a trivial group. So I won't tell you how it goes, why this C1 property implies this statement, but I shall give you an idea in the simplest case. So the idea of proof in dimension 4. So this is the following. Well, the simplest kinds of division algebras are generalized quaternions. So how do you define them? So you take A and B in K star, and then you define A and B, so this will be an algebra whose elements will be like this: x plus y to the I plus z to the, I'm just looking at my notation, is w ij, and the multiplication is given as follows, that I square is A, and j square is B, and ij is minus ji. So here you can see that it's non-commutative. And otherwise, so it's a four-dimensional vector space over K, right? And you extend the multiplication linearly. I have told you how to multiply these elements on each other. And so if you have an element here, so x plus yi plus zj plus wij, then you can associate it to its conjugate, which is x minus yi minus zj minus wij. And you can define its norm to be q times q conjugate, and you can say what it is. It's x square minus ay square minus bz square plus ab w square. It's like this. So you see it's a homogeneous polynomial in, in x, y, z, and w in 4 variables and of degree 2. Now the point is, so over a C1 field, it has a non-trivial 0 because it's of degree 2 in 4 variables. But notice that, in fact, what you can easily prove, that the norm function is multiplicative. So the norm of q1, q2 is norm of q1 times norm of q2. And therefore, norm of q is 0 if and only if q is not invertible. Because otherwise, I mean, if the norm is a non-zero element, then you can find an inverse for your element there. So this means precisely that there is, if over a C1 field, there is a quaternion which is not invertible, and that means it cannot be a division algebra. So this is the proof of quaternions, and the proof in the general case is similar. You construct a generalization of the norm, which has these same properties, and you give the same argument. But the general construction of this norm is much more difficult. Okay, so that was it. It's the reduced norm, yeah, exactly. So one reference for this is my book with Philippe Gilles on central simple algebras. Okay, so now in the rest of my lecture I shall discuss C2 fields.
The converse is not true, right?
Which converse?
Of this claim that, so what is the converse if the field is like that?
Oh, no.
So it's that the Brauer group is...
No, that the Brauer group is trivial does not imply that it's a C1 field. No, well, okay, so this is related. So the vanishing of the Brauer group is related to something which is called cohomological dimension in Galois cohomology, and so the vanishing of the Brauer group would imply cohomological dimension 1, but there are examples, non-trivial examples of fields of cohomological dimension 1, which are not C1 fields.
Would they be CR fields?
Wait and see. Yeah, no. So the answer to that question is also that there are examples where nothing is. Okay. So now I come to C2 fields. So here the condition is that n is bigger. The number of variables should be bigger than the square of the degree. And that will have to ensure the existence of a non-trivial zero. So can you give me examples of C2 fields? You already know some. Huh? Just, yeah? Concrete examples. Not the grown-ups, not the grown-ups.
For example, you have a power series with two variables or that. Very close to it.
You mean this one? You mean this one? That's not good. Because this is not the same as this one. So this one is good, this one is not good, okay?
Is the first C one? No.
Okay, so this is because this is a C1 field, and the length theorem tells me that if I take a power series field over that, that's a C2 field. Okay, so do you know other examples?
The receiver field.
Yeah, okay, but C2 fields which are not C1 fields. Yeah?
With the same idea, you can take polynomials.
Yeah, exactly. So CT T2, yeah, like this. CT1, T2. Well, instead of C, I could take, of course, any algebraic closed field. Okay, and then, so one last one is, of course, one which I'm most interested in, that if you take a finite field, and you form a Laurent series of the finite field, then that will be also a C2 field. Okay? So again, what I said that this has a discrete valuation, Vt. Also, so if inside this, you have the ring of integral power series. So these are exactly the x whose Vt is non-negative, right? Which are not do not have negative powers. And so it has a unique maximal ideal generated by T. All the others are units, as I told you, because if you have a power series whose constant term is invertible, then it's a unit, as I told you. And so this FQ T over T is FQ, so it's a finite field. Okay. Now there is another field which has very, very similar properties, namely the field of p-adic numbers. So in case you have not seen this, so QP, p-adic numbers. So in case I consider that this is part of sort of basic education. Everybody should see p-adic numbers once when studying math, but unfortunately it's not yet the case. So one way so let me quickly introduce them. So and you will see why they are similar. So you fix a prime number, p, and you take the product of all mod p to the n residue class rings, like this, okay? And so this consists of some infinite series, and inside you have the ring of p-adic integers, which consists of those series, let's say a to the n, which have the property that an is congruent to a n minus 1 modulo p to the n minus 1 z, right? So you have these coherent sequences. And in fact, there is a much quicker way to introduce them, but it's not obvious that it gives the same, that you take the ring of formal power series over Z this time, and you mod out by T minus P. So then you also get the p-adic numbers. So you can think of a p-adic number as being a sort of a power series in the pi, but this is of course in a formal sense and not in an exact mathematical sense. Okay? Yeah? Well, no, but I mean I want to take these from finite fields, because that you can also do. And that's just in a formal sense. But so here you also have a discrete valuation. Okay, so Vp of x, well, this is the smallest I, such that this pi is non-zero. Yeah, and you also have this ring also have a unique maximal ideal. Where should I write it? So Zp has a unique maximal ideal generated by P. The quotient is again a finite field for the P. And so the p-adic numbers are defined as the fraction field of this. And it's equipped with this discrete valuation. And it's also one analogy with power series, which I unfortunately, this is it's still here, is that it's complete, so any Cauchy sequence converges. So what are Cauchy sequences? Well, the point is that if you introduce a norm like this, then you can take any other favorite positive numbers of yours instead of E, it will be good. So with respect to this norm, you can introduce a metric, and in this metric you have Cauchy sequences, and then you can speak about convergence. And well, in both cases, you have this convergence property. So these, this shows that these two fields, I mean the power series, Lorentz series field over finite field and the field of p-adic numbers are really very similar. So Artin asked, is QP a C2 field? I mean, this is a natural question since the Lorentz series field is a C2 field, so is this a C2 field? And so the answer is, well, no. And so the first example was given by Terjanian in 1966, so it was some 30 years later. I write to you the simplest example, okay? So you take f of x1, x2, x3 to be sum of xi to the 4 minus sum of xi square xj square minus sum of xi square xj xk. So here this is I j over k. Yeah, so take the summation like this. But this is not it. You start with this polynomial. So this is a polynomial for the moment in 3 variables and of degree 4. And so then you take g of x, y, and z. So these are x1, x2, x3, y1, y2, y3, and so on. So it's 9 variables. And so this is f of x, plus f of y plus f of z. So this is still not it. The real example is age of x, y, z, t, u, v. So altogether it will be 18 variables. And it will be g to the x, g of x, y, z plus 4 times g of t uv. Okay, so this is 18 variables, degree 4, and no non-trivial 0 in Q2. This is an easy exercise, actually. Once I gave you, it's really easy to check that this has no 0 in Q2. And in fact, there are similar examples for any p, not just for 2. And what is worse is that, in fact, QP is not CR for any R. So there has been a series of papers in the 1980s proving this. So this is very different. But to return to your question, it is of cohomological dimension 2. So there's really but not CR for any R. Okay, so that's not good. So what then how can you remedy this?
So what's known about the smallest number of variables? Is it like algebra stuff? So given a degree, what's the small?
Well, as I say, there is no.
It grows faster than.
I don't know whether it was. Yeah, I don't know whether this has been investigated. I don't know.
I'm sure it is.
Well, it has been certainly, but I don't know. Yeah. Yeah, I'll cite some results of Heath-Brown in a moment, okay? But it will be at a different time. So what are positive results? So one is a result of Kato and Kuzumaki in 1986, who proved the following. Kuzumaki is actually a woman. You won't tell it from her name, but so for every f, so every form f of degree d in bigger than d variables, there exists finite extensions k1 and so on, kn of qp, such that f has a non-trivial 0 over all ki, but and if I look at the greatest common divisors of the ki over qp, it is 1. So obviously, this is a generalization of the property of having 0 in non-trivial 0 in QP. But so this is really a natural condition from the point of view of geometry, because I mean, typically it shows something. If you have a quadric will have a 0 over a quadratic extension. But so it may be that if you have a quadric over the field, then it will have only zeros only over extensions of even degree, sorry, but perhaps not over extensions of odd degree. And this has that if you have a family of, so at least you can assure that it will have zeros over extensions whose degree are co-prime to each other. So it's really a stronger result than what, and it's quite non-trivial to prove. It's elementary but non-trivial. Okay, and so this is one thing, and the other thing is much more well known, and it is the theorem of X and Cochin. It's the 1960s, which says that for fixed D, homogeneous polynomial, in fact, over Zp, in bigger than d square variables has a non-trivial zero for p sufficiently large. So for all but finitely many p, you have this. And so, for instance, Heath-Brown has results for specific polynomials where he can control the exceptional set. This result is not effective. It does not tell you how long you have to search for this p, but in some cases, analytic number theorists can do this. And so the point is that so the original proof of this theorem was based on mathematical logic. And this is what I want to explain briefly. So it follows from what is called the X-Cauchy transfer principle. So what's this? Well, it says that a first order statement about rings is true over Zp for p sufficiently large if and only if it is true for Fp T, form a power series for p sufficiently large. So what's a first order statement? So I'm not a logician, but so this is a statement which you can formulate about rings, and it has their usual quantifiers, yeah, so everything and existence. So for instance, having a solution is typically a first order statement. So you see immediately that, I mean, since we know that this is a C2 field, then the transfer principle will say that for p sufficiently large, it will also have a zero in Zp. So as I said, I'm not a logician, but let me just give you the idea of how this comes out, because I've made already quite a lot of preparation for this. So it uses ultra products. So I won't tell you what ultra products are, but so for those who know, so you take non-principal ultra filter on P, which is the set of primes, containing cofinite sets. And then you take, let's say R, I don't know, R to be the ultra product, for P in P, of all ZPs modulo. So this ultra product will be a certain quotient of the direct products following this ultra filter I have chosen. Okay, and let's say R prime will be the same thing for the modulo, the equivalence relation. The same thing for the power series ring. Now, so for ultra product, there is a basic lemma due to whoosh, which says that the first order statement is true in the ultra product if and only if it is true almost in almost everywhere each component. Okay, so this means that typically in this case, so if a polynomial has a zero in Zp for almost all p, if and only if it has a 0 in the outer product. And the point is that so if you take the fraction fields of these ultra product, so they have a discrete valuation. Well, actually not a discrete valuation. They have a valuation which may not be discrete. Well, this is because this is also a first order statement. So it's a valuation satisfying the same rules. So with same residue field, and I tell you what it is. This is the outer product of all finite fields from OP. So that's the field of characteristic 0. And also the same values. And they are complete. And so then it's a theorem that whenever you have two complete valued fields with the same residue field, the same values, then any first order statement which is true in one of them is true in the other. This is what is called elementary equivalence in logic. So they satisfy the same first order statements. Okay? And so that's the proof. So you start from these where you know the existence of a non-trivial 0, you pass to the ultra product. Now the existence of this of 0 holds in the ultra product, so you can go over this side, and then you go back to each component, and that will.
I'm confused. So what is that is true for a big set in terms of ultra filter, but why is it true for every large enough prime?
Well, because we took the cofinite sets in the ultra filter.
But there will be other large sets for sure, like the odds and the evens. One
Mhm.
of them will be in the ultra filter.
I think it goes the other way. You have to negate this.
Yeah, yeah.
Right. So you're negating the statement.
Yeah. I just wanted to simplify the thing because there are a lot of things which I did not explain. Yeah. Okay, but I still, well, I've a little more than 5 minutes, and I still haven't spoken about geometry. So I've spoken about logic, so I'll speak about geometry.
So you negate it and you take the set of counterexamples.
Yeah. You take the intersection of the outer filter with the cofinite sets. And, yeah. Okay, so geometric reformulation. So this is the following. So consider now this a homogeneous polynomial. So it will have some coefficients like this, and so the sum will go to over EI such that the sum of D. Yeah, this is like a general homogeneous polynomial. And so you consider these as indeterminates. So then you have how many indeterminates? So I believe it's n plus d choose d. So these are the possible number of possible monomials. And so you can reformulate. So this thing defines. So, and you want to look at the zeros of this homogeneous polynomial. So that's a homogeneous polynomial equation. And so from a geometric point of view, it defines what is called a hypersurface. So an algebraic variety defined by one equation in the projective space in n plus d choose d coordinates times the projective space in n coordinates. Yeah? So these are for the c's and these are for the x's. So for those of you who have seen algebraic geometry, you know that this product is not completely obvious to define, but let's pass over that. And so let's call it H. Yeah? And so what does X-Cotchen say? Well, X-Cotchen says that if you look at the first projection, yeah, so here we have two projections, to the p to the blah, 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 and the other projection to the p to the n minus 1. So it says that the first projection from H, and you plug in values in ZP to p to the n plus d choose d minus 1 ZP. So this is surjective for p large enough. This is what it says. Because what's the point here? Well, this is giving concrete coefficients for a concrete hypersurface, and the surjectivity means that it actually has a point, because I can fill in the other indeterminates as well. Okay, so this is what it says. Now, this is a nice geometric statement. So you can, therefore, formulate a geometric version of the transfer principle, which is called the surjectivity principle. And which is the following. So now I'm using the language of algebraic geometry. So for a morphism x to y of z varieties, so morally these are objects defined by a bunch of polynomial equations in some space locally, and a morphism is something given by polynomial map. There's a polynomial map between them. X to the zp to y to the zp is surjective for p large enough. So this holds if and only if x of fp t to y of fp t is surjective for p large enough. Okay? And so if you apply this to this special situation, you get a new proof, you get another proof of X-Cotchen. But of course, this statement is a special case of the transfer principle, so you can reformulate this as a statement of over rings. However, what is different here, that very recently, Jan Denef gave a purely geometric proof. No logic. No. No, it's not effective. It's not effective, but it's really in the spirit of algebraic geometry, namely that, so you have to study the fibers of this morphism, so fibers of the inverse image of a point. And so if the fibers are what is called smooth, then you get away very easily, because then then there's a tool which is known as Hensel's lemma, which helps you in finding solutions. And the whole idea is to modify the situation such that it becomes, in a geometric way, such that the fibers become nice, so that you can apply this. And that's the difficult part, and that uses results about resolution of singularities in algebraic geometry, and so on and so on. So, and Hironaka is not enough. You need newer ones. And so I want to finish by one more statement, because this is not just, so Denef proved something more. So he also proved the following theorem, which I won't state in a very precise form. So if phi x to y is a morphism of smooth projective varieties, let's say over Q, such that whose fibers are sufficiently nice So I won't tell you what sufficiently nice is. So it's a technical condition, but it's purely geometric. It's formulated in terms of geometry, that the fibers are not very bad. So then it follows that on p-adic points, so this is surjective for p sufficiently large. And in fact, this was a conjecture of Colliotelin, who checked that the fibers of this particular thing, h to the p n plus d over d minus 1, are nice. Okay, so this condition holds in this particular case, which I was describing here. And so if once you know that this condition holds, then you can apply this theorem to get yet another proof of X-Cotchen in a much more general situation. So just let me give two more comments and I'll finish. So one is that checking that this condition holds for this particular morphism is absolutely non-obvious, and it uses a recent theorem of János Kollár, which uses deformation techniques in algebraic geometry. So it's really something really hard, even if it's completely explicit. And the other thing is that, so if you compare these two theorems, so they are really different in nature, because this is still a transfer principle, so you want to transfer something from characteristic P to characteristic 0, but here there is no transfer. You have a purely geometric condition and you have what you want. So they are really completely different in nature. And still, both approaches are valid, so you can approach the same problem using logic, using geometry, or by a combination of the two. Okay.
Thank you. Are there any questions or comments?
Yes. About this theorem, which has some proof using logic and another pure algebraic proof.
Yeah.
I'm of those people who are believing that any statement in logic can be written in some equivalent algebraic form and can be proven algebraic.
Yeah.
So for me, because I'm saying this because, for example, some persons were surprised when there is pure algebraic proof without logic, but for me it wasn't surprise because I think any statement in logic can be done.
Yeah, so it's good that you mentioned this because, this has been a recent, but look, even for this, we waited 30 years. X-Cotchen, or 40 years. So X-Cotchen was in the 60s, and this geometric proof was found now. So most people have the feeling, like you, and in fact there has been a recent trend in algebraic geometry that we use techniques from logic for proving geometric results, and once it is proven using logic, then a few years later someone finds a proof without logic. But it's not so. We also always have to run behind. In particular, there is one very strong guy called Ehud Khrushchevsky who has proven many very deep theorems in algebraic geometry using logic, and some of them have been proven using geometry, and some of them are still open. And the point is that in this example, so I did not speak about the proof itself, but the nature of the proof is completely different. So it's not just you are translating the argument which it comes from logic in some language without logic. You really have to find something else. So I'm not contradicting you. Most people have the same feeling, but this is sort of a heuristic rather than a rule. And we still have some theorems, some deep theorems in algebraic geometry for which the only known proof uses logic.
It is not just a feeling. I'm working in this.
I know, but you're not the only one. It depends on.
I like algebraic proof because there is some pure
Mhm.
There's a beauty to them, and I like them because of that. And you know, if you break away from using ultrafilters, but basically are using the same idea that while you're using, I still think about it as an ultrafilter argument in my head. I don't care whether you use the axiom of choice or not. But that's my take. I mean, that's a personal note. But this must be, I mean, from what Tamás says, this is a different proof.
Yes, it's really a different proof. So you cannot adapt. So it's not just. So I agree that for most elementary statements, what you're saying is true. But these are, yeah. So once you go to a high degree of difficulty, I mean, this becomes only a heuristic. And in fact, so I was at a conference in March in Rényi, where we tried to understand a very difficult theorem by Khrushchevsky, which uses logic and proves something in geometry. And so it has been on for 10 years, and now after the conference, some people claim that they can do it without logic, but it's after I don't know how many years of very hard work. So
same here, in group theory.
Yeah.
Khrushchevsky proved cool stuff in group theory. People are trying to grabbing the hold on that for decades. So
Yeah. So probably what you're saying is true, but yeah.
So any more questions or comments?
It's a very simple question. So,
Yeah.
what happens when the fibers are not as nice? Are they counterexamples?
Yeah. You don't accept. Of course, you don't expect this to hold in full generality. You need some condition on the fibers. Yeah. But I did not tell you what the condition is.
I saw that there was a motivation for the C1 fields.
Yeah.
Is there a motivation like that for C?
So CR fields are always of cohomological dimension R. So if you, this means that. Sorry. Huh?
CR fields have cohomological dimension
R. At most R. Yeah. And so it's useful in proving, for a concrete field that what its cohomological dimension is. But there are counterexamples the other way.